This clip is the second part of the lecture of Chapter 4 on the analysis of statically determinate beam and frame. And the next section we are going to talking about the shear and bending moment diagram of the beam. Beam are mainly designed to resist both the bending moment and transverse shear force. So it is important for us to draw the shear diagram to determine the maximum shear force and also determine the maximum bending moment to determine the bending moment diagram to obtain the maximum bending moment. The shear and the moment are the function of the position x along the beam axis. So we can use the method of section to cut the section of the beam and then use equation of equilibrium to determine the function of the beam. Okay, and then by cutting the beam, then draw the free body diagram, the shear force and the bending moment can determine by the equation of equilibrium. For this one is the triangular uniformly distributed load, and it has the shear force like this, and also it produces the bending moment diagram like this. The shear diagram we use to determine the Vmax. The bending moment diagram used to determine the maximum bending moment, and we will be talking about this later. Okay, for the procedure of analysis, we start by considering the whole beam, and then we draw the free body diagram of it, and then we use the equation of equilibrium to find the reaction. For this beam, it's a symmetric beam and is subjected to the 5 kilonewton here, so the reaction at A is 2.5 kilonewton and at C also 2.5 kilonewton. If you like to find the function of the shear force and the bending moment, you got to set the coordinate. Usually the coordinate is set between some specific point, like this one. We set the first portion is the AB and another portion is the BC, so we have the x1 and x2 to determine the function of the shear force and the function of the bending moment. If you cut the beam by x1, just cut like this, you will get the portion of this beam, and then the x1 can use from A, which is 0, up until B, which is 2 meters. So x1 will have the interval of 0 equal to less than or equal to x, and x less than 2 meters. And then if you summation of x sub y, f sub y equal to 0, v will equal to 2.5, and the m will be equal to, m rotate like this, 2.5 x1. So you can get the function of the shear force and the bending moment easily. Also, if you cut at the x2, see, you just take the cut here and then you draw the free body diagram. This going to start by point B. So the x2 gonna start here when the x is equal to 2, and then x2 can extend up until point C, which is 4 meters. So this portion of this beam, okay, use the x2 between 2 and 4, and then summation f sub y equal to 0, v plus 5 equal to 2.54. So the v is going to be minus 2.5. And then you also can take the moment here to obtain the function of m. Okay, so we have the function of the shear force as the v sub x and m as a function of x. And we can plot the shear diagram. As I mentioned before, the shear here is positive and the shear here is negative. Okay, and also the moment here is 2.5x2. That means if x equal to 0, it is 0. If x equal to 2, that is going to be 2.5 times 2, that is 5 kilonewton meter. And then you can find V max to be plus and minus 2.5 and M max of 5 kilonewton meter. Okay, now let us to take a calculation, take an example of some important beams. First, this is the simple beam. Okay, we will draw the shear diagram and bending moment of this beam. This beam is subjected to uniformly distributed load between A and B. And between B and C, there is no forces. And at B, we have the clockwise moment of 50 kilonewton meter. And by the A is the pin and C is the roller, we can draw the free body diagram of this beam like this. The A gonna have A sub x and A sub y. The C gonna have C sub y. And by using the equation of equilibrium, summation of x sub x equal to 0, and then we get A sub x equal to 0. And then we take moment at one point. Let's take moment at C. Okay, we will see. And the counterclockwise is positive. That means the A sub y produce the moment about C with the clockwise direction. So A sub y gonna times 10 and have the negative sign. Okay. And the uniformly distributed load, this is gonna have going to be equal to the area of this uniformly distributed load. That is going to be 2 times 5, and it's going to act at the centroid of this area. So the length here is going to be half of the 5. That is going to be 2.5 meter. And this 10 kilonewton resultant force gonna rotate like this, counterclockwise. So this one will produce the positive moment. And then the 50 kilonewton is rotated clockwise. This is gonna be negative. Okay, so let me conclude. The A sub y times 10 rotates like this. Minus. And 2 times 5, the resultant force gonna rotate counterclockwise, going to be positive with the moment arm of this is 5 over 2 and this is 5. So we have the total of 7.5. And this is clockwise moment, so it's negative. So we get A sub y equal to 2. And then last one, summation of f sub y equal to 0. The C sub y upward, the 2.5 upward is going to be plus, and then 2 times 5 downward, so negative. You get C sub y of 7.5 kilonewton. So we get the free body diagram of the beam like this. Since the beam can be separated into two portions or two segments, the first one is between A and B, that's cover the uniformly distributed load. And then another portion is between B and C. So it's up to you how to set the coordinate x1 and x2. If you set x1 like this, that means x1 start from here, 0 meter, and then it's going to increase 1 meter, 2 meter, 3 meter, 4 meter, and 5 meter. So the length of x1 is going to be between 0 and 5 meter. Okay, and it's going to be in equilibrium due to the bending moment M and the shear force V. And then for the second one, this x2, since the x1 cover the length of AB already, so x2 will start here. If x2 start here, that means x2 start by x2 equal to 5 up until 10. 10 of what? 10 of point C. Okay, we also have the shear force and bending moment at the cut section. Okay, again, summation of f sub y equal to 0. You can see v downward, so it's opposite to this direction, so v is negative. And this one also 2 times x1, the resultant force is going to be 2 times x1, and it's downward, so this one is negative, this one also negative, and this one going to be positive. Okay, so the v is equal to 2.5 minus 2x1. And if x1 equal to 0, the v gonna be 2.5. The v gonna be the same as the reaction here. Take the moment at the cut point, this point. You will see that the m counterclockwise. 2 times x1 gonna time x1 over 2 and counterclockwise. So this moment and the moment due to the resultant force gonna have the same direction. Okay, and 2.5 times x1 gonna have the opposite direction. So if we set m is positive, so the moment due to this red resultant force is also positive, and the reaction A sub y produce the negative moment, and you get this. Okay, and you may see some important thing from this equation. When we have the uniformly distributed, look here, the equation of the shear force is the linear function, and the equation from the moment is second order polynomial equation. Okay, it's up by order from constant to linear equation to the second order polynomial equation. And then you cut here to find this. We start by summation of the force f sub y equal to 0. Okay, between B and C, that means x2 can be 5 meter to 10 meter. And then we set upward is positive, so this v is negative again. The resultant force here also 2 times 5 is negative, and this guy 2.5 kilonewton is positive, so 2.5 positive minus 10 minus v, you got v equal to minus 7.5. And we take the moment at the cut point. If this moment is positive, we will have this what? This is 10. 10 gonna time the distance between this green arrow to the red point. And how long is this? The length between this is going to be x2 minus this. This portion gonna be half of 5 meter. Okay, and then the moment gonna rotate in the same direction as m, so m plus, this is the red force, sorry, this is the green, the light green, 2 times 5, and then times the length of x2 minus 2.5. The last one, 2.5, the A sub y gonna rotate in the opposite direction as the M. So it has minus 2.5 times x2. And also don't forget about the 50 kilonewton. This is opposite to the M. So it's negative. So you get the function of moment in this form. Okay, let's make a note on this. There is no uniformly distributed load here. And we can see the V is a constant. And the M is the linear function. See, it steps up by one order from the load to the shear, from the shear to the moment. And finally, we put all the equation, we put it. And then we will see by separate this one from 0 to 5. This is from A to B and from B to C. And if you put into the equation, if x equal to 0, this is 2.5. If x equal to 1, 2 times 1 is 2. This is 2.5 minus 2 is 0.5. And then if this one is 2, 2 times 2 is 4. That is 2.5 minus 4. You got this. If you put everything, you get all the value here. And then for the length of x2 from 5 to 10, the shear force is constant. And next, for the function of the moment, you also get this for A to B, and this from B to C. And if you plot the graph, you're going to get the shear graph, shear diagram like this. And then for the moment, you got this as the moment diagram. So what is going to be the Vmax? Vmax is going to be minus 7.5. What is going to be the Mmax? Mmax is going to be 37.5 kilonewton meter. Okay, and then you use the Mmax to decide the section of the beam. And after you get the section, you check that section can take the Vmax or not. Okay, let's make some important point. We can notice that when this force is upward for 2.5 kilonewton, okay, and then we get what? We get the shear force up to 2.5. And when this one is minus 7.5, you get C sub y of 7.5 just up. So at the acting point of the upward point load, the value of shear diagram is positive or increase equal to the magnitude of the point load. And also it's going to be in opposite. If it's downward, the value of shear force at that point going to be decreased or downward. Okay. Okay, and next, the bending moment. The clockwise bending moment produce what? Produce the bending moment from minus 12.5 to plus 37.5. So we can conclude that at the acting point of the clockwise couple moment, the moment diagram is increased equal to the magnitude of that moment. So clockwise moment make the increase or make the positive moment at that point. And if you further consider, you may see that the first term dv by dx1, it is dip with respect to x1 equal to 0. If we dip this with respect to x1, it's going to be minus 2. Minus 2 is minus the uniformly distributed load. And if you dip this, it's going to be 0. So that means there is no uniformly distributed load between B and C. And the second one, dm by dx is v. If you dip this one, you can get 2.5. If you dip this one, it's going to be get minus 2x1. See? And also this one, if you dip this one, you get minus 7.5. and if constant is 0, see the dm by dx equal to v. These relationships are important, and we will conclude this note, and then we will use this relationship to draw the shear diagram and moment diagram by the graphical method. That's going to help you because graphical method is easy to use, more flexible than cut the section, write the function of the shear, write the function of the moment, and then draw the diagram, and then draw the table, and then draw the diagram. That is really time consuming. For the graphical method, that we use this kind of relationship, we can draw the shear diagram and moment diagram directly. Okay, go to the next example. This example, like the previous one we discussed before, is subjected to the triangular uniformly distributed load of 1.5 kilonewton per meter. The B is pin, they're going to have B sub x and B sub y. The A is roller, we're going to have A sub y over here. And by drawing the free body diagram of this beam, using the equation of equilibrium, we will get the reaction. And then if we cut at one point, okay, when we cut at one point and when define the coordinate at this point as x, this time we have only one x. Unlike previously, we separate the beam into two sections because the load applied to the beam is this continuous at B. So we separate the beam into AB and BC. But this one, the load continuously distributed along the whole length of the beam. So when you cut here, you can determine the function of shear force V and function of bending moment M. And this problem, you're going to get only one V and one M. And then you can draw the shear diagram and moment diagram. Okay. By doing this, we start the free body diagram here. Summation of x sub x equal to 0, b sub x is equal to 0. And then if you apply summation of f sub y equal to 0, you didn't get the result. You should use the equation of moment. So let's we take the moment as b here, and you take the moment here, and the counterclockwise is positive. That means a sub y gonna time 3, and it's going to rotate clockwise about b. So that moment is negative, right? And then this is the resultant force of the triangular uniformly distributed load. This is equal to the area of the triangle. Okay, 1/2 of 3 times 1.5. And then it's act at the centroid of its area. That is going to be the length of the beam divided by 3. So it's going to be 3 by 3. This is going to be 1. The moment of this green force going to rotate counterclockwise. So this is going to produce positive moment, and this is going to produce negative moment like this. So you get the A sub y of 0.75. So now, if you use the summation of f sub y equal to 0, the b sub y upward, the a sub y equal to 0.75 upward, two of them upward, the green resultant force downward. So you get the v sub y of 1.5 kilonewton. And you also see that this is makes sense because the triangular load have most or portion of its area near B. That's why B sub y is larger than the A sub y. Okay. Now, due to the continuous of triangular distributed load, we just have one cut over here with the coordinate of x. And then we use the same sign convention as before. The shear downward is positive. The moment counterclockwise is positive. The problem is how to find this magnitude of triangular uniformly distributed load as the x. So we use the similar triangle, okay? And then we proportional it like this is W divided by x, and it's going to be 1.5 divided by 3, and then W is 0.5x kilonewton per meter. It's a function of the triangular uniformly distributed load. If x equal to 0, see, this is 0. If x equal to 3, this is going to be 3 times 0.5 is 1.5. And if x is 1.5, okay, this is going to be 1.5 divided by 2, that is going to be 0.75, for example. Okay, let's use the equation of equilibrium. Summation of x sub y equal to 0 upward is positive, so this guy is going to be negative. And the area here going to produce the resultant moment of 1/2 of x times 0.5x. So this is going to be the resultant of this force, and it have the same minus, and this guy going to be plus, so it's going to be plus 0.75 minus the resultant of the triangular loading and minus the shear, and then you get this equation. And then if you take the moment at this point, then the moment rotate counterclockwise, and this resultant force also produce the counterclockwise moment. So m plus this value times this one is going to be x3. So this one will be x over 3, and then you get m plus the resultant of triangular area times x over 3, and then 0.75 rotate clockwise, so it's going to be negative. It's in opposite of the m, and then you get this equation. And let me make a note again. If you recall from the previous example, when there is no uniformly distributed load on the portion of the section BC of the beam on the previous example, we get the W equal to 0, and the shear is a constant, and the moment is the linear equation. And then on the portion BC, there is the uniformly distributed load of 2. Okay, and then we get the function of the shear as linear function and function of the moment of the second order polynomial equation. And now our uniformly distributed load is linear function. The shear is the function of second order polynomial, and moment is the third order polynomial function. And you may see the function gonna increase by 1 order from the load to the shear, and 1 more order from the shear to the bending moment. And then again, if you plot the graph, you got to set the x along the length of the beam, and put the x into the function of v, and put the x into the function of m, and then you got this graph. And by taking a look at this graph, and we have the function of v in this form, and you may see if x equal to 0, that is this point. What is this? Is 0.75. Is equal to what? Is equal to reaction at A. And if you put x equal to 3, that is going to be 9, okay, and 9 times 9 divided by 4, okay, you may get this one as 2.25, and minus 75, you get this of minus 0.75 minus 2.25, you get minus 1.5. This means the shear force changing from the positive to the negative. So there is some point between the support A and support B in which the shear force is 0. How can we determine that location? So go back to this equation. At this location where V is 0, just put V is 0 and then you compute by the x. You got that position is 1.732 from the point A. Okay, and then after we plot the moment by putting the x from 0 to 3, and we get the graph like this. Okay, and if we like to determine the moment max, okay, and then we just put the 1.72 into the moment equation, and maximum moment is going to be 0.866. So maximum moment is occur at shear equal to 0. Why? Because if you remember, dv by dx equal to, dm by dx equal to v. It means dm by dx is the slope of the bending moment is equal to shear. If shear is 0, that means the slope of the bending moment is 0. When slope of a function is 0, it will produce the maximum value or minimum value. And then we have, as mentioned before, dv by dx equal to minus of the uniformly distributed load. If you dip this is 0, and this is going to be 2 times 0.25 is going to be 0.5, and x. 0.5x is w, and this is negative. And if you dip m, the first term going to be 0.75. The second term going to be 0.0833 times 3, and then x power 2. And then you're going to get this. So dm by dx equal to v. And the most important, as the point of zero shear force, the moment at that point is maximum or minimum. Okay, another example. This example going to show you the beam with 3 interval. When the beam with 3 interval, that means you will cut beam for 3 times, and you will get 3 shear force equation or function, and you also have 3 bending moment equation. So when you get the beam with many interval, the calculation to draw the shear diagram and the moment diagram by using the equation will be very cumbersome, inconvenient. Anyway, let me show you like that. We know that the free body diagram of the whole beam. So A is pin, have A sub x and A sub y, and C is the roller, has a C sub y. And by doing this, the uniformly distributed load is 100 kilonewton per meter, and it is in the range of 0 to 5. And then between 5 to 10, there is no uniformly distributed load, but we need to select this as a portion because it blocked by the 1000 kilonewton. And then from 1000 kilonewton to the support C, this is going to be another section. So if we set for the coordinate x1, you may set this one for the coordinate x2, and you set this one for coordinate x3 later. Okay, let us summation of x sub x equal to 0, a sub x is 0. And if you take the moment at a, counterclockwise is positive, so c sub y gonna rotate counterclockwise, c sub y gonna time 15. So 15 c sub y is positive. And then the resultant of the uniformly distributed load here is going to be 100 times 5, and it's going to be 2.5 meter from the A. And the rotation clockwise, that's negative. The 1000 kilonewton are 10 meter far away from A, and it's going to rotate clockwise. So we have the C sub y that produce positive moment. The 1000 kilonewton times 10 produce negative moment, the green, and the red also produce the clockwise direction, which is negative. Okay, it's going to be 100 times 5, and then times half of 5 meter, and then C sub y is 750 kilonewton. The last one, we summation of the force in vertical direction. The upward A sub y is positive. C sub y of 750 also positive. And then the resultant force, the red one, is negative. The green is negative because these two downward. And then you got A sub y of 750 kilonewton. Okay, now we have 3 portion, 3 interval. So we need to set 3 coordinates. Let me separate. This is going to be x1. And then from here to here going to be x2. And from here to here going to be x3. And x1 going to be from 0 to 5. And x2 start from 5 to 10. And x3 from 10 to 15. Okay, put the reaction over here, and it's going to have the applied force here. This is not going to be in equilibrium. We have the internal shear force and internal bending moment, and set this one as x1. And then you use summation of f sub y equal to 0 for the length of 0 to 5. And v is downward. Okay, v is downward. And it's going to be equal to 750 and minus 100 x1. Okay, and then we get this equation. Taking a moment at a cut point, and then we get what? The m in this direction is equal to the opposite, 750 times x1, and then minus 100 x1 times x1 divided by 2 is minus, because when it's on the left hand side is plus. Okay, it's in the same direction as m. When you move the opposite side, change to minus, and then we get this equation. Okay, and the second one, we have this as a x2. By doing it the same, summation of f sub y equal to 0 for x2 for 5 to 10. We have the v is downward. Okay, it's going to equal to the opposite, 750, and minus this one. So in this section, the v is constant of 250 kilonewton. And then do summation of the moment at the cut point. So this m is clockwise, is opposite by 750 times x2 is equal to this one. In opposite is hit each other. And then minus this one. How far of this one to the cut point? is going to be x2 minus 2.5. Okay, that's going to be x2 minus 2.5. And then you get the m of this. And this term can be reduced to 250 x2 if you like later. Okay, for the x3, we have x3 here. The same apply. Summation of f sub y equal to 0. You get the v is downward, is equal to 750. And then minus this, and then minus this. Okay, is minus again because it's going to be v plus 100 plus 100 times 5 equal to 350. And then you move this one from plus to minus, from plus to minus. The shear going to be minus 750 kilonewton. And then the m, you take moment the same here, and the m is here. So it's going to equal 750 times, this is clockwise, this is counterclockwise, this is going to be equal to. And then since this one rotate in the same direction, so when it's moved from the left to the right, it's going to be negative. Negative of what? 1000 times the distance here. The distance here can determine from where? From x3 minus 10. Okay. And also the 100 times 5 gonna rotate in the same direction as m. When you move to the right hand side, is negative. The distance from this point and to this point and this point is going to be x3 minus 2.5. Okay, and then you got this equation. Again, this is going to be 1250 x3 minus. Okay, in conclusion, the first cut when x1 equal to 0 to 5, you get these two equations. For the second cut, the coordinates x2 from 5 to 10, you get this set of equation. And the last cut from 10 to 15 for the x3, you get this set. And then you may put this shear diagram portion. If x equal to 0, this is going to be 750. If x equal to 5, this is going to be 750 minus 500, so it's 250. And then between this, we get the shear equal to plus 250. And between this, if you remember, we get the shear of minus 750. This is the shear diagram with the maximum of plus and minus 750 kilonewton. And for the moment diagram, there is no external moment at A and at C. So the moment at that's 2 points going to be 0. From the first equation, if x equal to 0, you see, we got 0 as I mentioned before. And then if x equal to 5, you got put 5 into this equation and you get a curve like this. And the best practice is when you plot any portion of this, you got to point the start, point the end, and you point another one point in between, so you can separate between the linear line and the curve line like this. And you can see this is the portion of uniformly distributed load with constant W, and the shear is the linear equation. The moment is the curve with the polynomial second order equation. And then if this one is 250 is a constant, since this portion, this x2 portion, has no uniformly distributed load, and this one constant, so the moment going to be linear equation. Okay, the equation is like this. If x2 is 5 times this is gonna be 1,250. 1,250 plus 1,250, you got 2,500. And if 10, this one going to be 2,500 plus 1,250. That is going to be 3,750. You got this as the linear function. And the last one is easy because this one going to be negative. So the moment here will reduce, and you know that this is the roller without external moment. So the moment at this point gonna be 0. And if you like to check, you just put the x of 15 times 750. This term going to be minus 11,250, and then you get this as 0. Okay, in conclusion, again, we have some note. The dv by dx equal to minus w. This means if you dip this term is 0. If you dip this term is going to be minus 100. Minus 100 is minus w. And over here, v is constant. If you dv by dx is going to be 0. And this one also is going to be 0. Second, the dv by dx equal to v. Okay, if you dip this one, the first term, you dip this with x1, it's going to be 750. And if you dip 50x1 square with respect to x1, it's going to be 50 times 2, and it's going to be 100 with minus sign here and x1. See? Also this one, if you dip this one is 0. If you dip this one, it's going to be positive 250. For this one, if you dip this one is 0. If you dip this one, going to be negative 750 is equal to this. Okay, and then the downward point load produce the negative. As you can see here, is reduced from plus positive 250 to negative 750. That is 1,000 equal to this. And at this point also is have the the upward reaction of 750, and this is also had upward. So upward, that means that shear gonna be increase. The downward, the shear gonna be decrease. Okay. Okay, that is the end of clip 2 of chapter 4, the analysis of statically determinate beams and frames. And then what we have discussed in this clip, we draw the shear diagram and moment diagram of the beam by using the shear equation and using the bending moment equation. How the shear equation and bending moment equation come? It comes from the free body diagram of the portion of the beam with the coordinate x, and then we use the equation of equilibrium with the free body diagram to determine the function of shear force and function of the moment. The first example, we cut two portions. We got two equations of shear force and two equations of moment. The second example, we only need to have only one cut or one coordinate. We got one shear equation and one moment equation. That's really easy and convenient. However, the last one, the beam separate into 3 segments, and now you're going to cut 3 times and use the equation of equilibrium 3 times to plot the graph. That is inconvenient. But during the 3 examples, the first, the second, and the third, we have some important relationship between the distributed force, shear force, and bending moment. That relationship we'll use in the graphical method to draw the shear diagram and to draw the bending moment diagram. So the next clip we're talking about that.